Okay, welcome back to lab number 7. We're moving right along, having trouble talking here, and this is called a moving charge in a uniform B field. And it turns out if you can create a uniform magnetic field, by the way, I usually call it a B field, because that magnetic field is about this long, B field is only this long. All right, so this picture right over here is an electron beam that is in a uniform B field. And it turns out that if you can create a nice uniform B field and you create an electron that's moving in a nice straight path perpendicular to the B field, it'll go into a circular path. So this is called uniform circular motion using a charge interacting with a B field. And this force between charges and B field was first mathematically stated by a guy named Lorentz. And it's called the Lorentz Force Law. And he lived at the same time as this other guy named Thomson. And Thomson took this information and he made a hypothesis. He hypothesized that this colored light, this light coming off of this beam, was due to particles. It wasn't light, because light doesn't bend in a magnetic field. So how is this beam of light bending? So he said it's due to charged particles that are interacting with the magnetic field. Now, this is sitting in an enclosed space that's evacuated, which means there's no air inside the space where this is contained. All right? And if I go ahead here, you can see this globe right here. That globe, this is called an E over M tube, an E over M tube, and it doesn't have any air in it, a little bit of helium, that's about it. But for the most part, it's a vacuum, a really good vacuum. All right? So this beam is created inside that tube by interacting with the B field. All right, so I got a picture on the board right over here. And I'm going to pick, for this case, a positive charge. So it's a positive charge right here, and it's going to go into a uniform magnetic field, and the magnetic field is pointing into the board. All right? Now, when you create a uniform a magnetic field, any kind of magnetic field, the magnetic field fills space. That's why they call it a field. So like if you sit here on the board, this magnetic field is filling this two-dimensional space right here, just like a farmer would put in his rows of corn. Well, here we got all these X's that represent the magnetic field going into the board. Now this is the back end of the vector, because B field is a vector, so we use X's. If the B field were coming out of the board, we'd use a dot like that. And because a vector is an arrow, we normally draw it like this, so you see it's got the little point on front, so that'd be coming out of the board, and then in the back it's got feathers, and so you're looking at the feathers right there, the back end of the feathers. So this is a B field into the board, and here's the charge moving to the right. Now Lorentz came up with the force law, the kind of force that a charge is going to feel that's moving in a B field. By the way, if a charge doesn't move in relation to a B field, there's no force at all. Also, if a charge is moving parallel to a B field, no force. No force at all. They discovered that. No force at all if the charge is moving parallel to the B field. So if the charges were moving into the board here or out of the board, nothing would happen. It would just go nice and straight. But here I got a nice perpendicular angle between the B field and the velocity, and you're going to see the maximum amount of force. Well, vectors that behave this way are called cross products. Okay, this kind of force law is a cross product. because it depends on the angle between the two vectors. And as a result of that cross product, you get another vector, and that's the force. Okay, so the force law looks like this. It's the charge Q, which is a scalar, and then the velocity V cross B. V cross B. And we studied cross products with torque where we did R cross F and found the torque. Well, this time we're going to find the force. And we use the right-hand rule a little bit differently in this case because you see the B field is all spread out. So we take our fingers, our 4 fingers right here. And since the B field's into the board, we use our fingers and put them in the board. Now the velocity vector is a single vector, so we use our thumb for the single vector right there. And so I put my fingers into the board, my thumb in the direction of the velocity vector, and out of the palm of my hand comes the force. Okay, and that force would be directed upward like that. All right, so may the force be with you. All right, you're probably cursing me right now, but that's okay. Anyway, so let's go ahead and see what happens when this comes into here. So when it comes into here, it's going to feel a force up like that. Okay? Then what's going to do? Well, if a particle feels a force like that, it's going to start moving in that direction like that. Well, let's go look right there. Well, now it's got a velocity vector that's pointing in this direction. So you take your fingers, put them in the direction of the B, and then your thumb along the V like that, and you can see the force is in like that. All right, so that means it's going to go like this, and it's going to make it go like this, it's going to make it go like this. So you can see it goes into a circular path. Like that. And there's a radius of the circle. Nice, huh? So now we can write this thing. This is Q, V, B, sine theta, but we want the maximum force possible. So we made theta, we made the angle 90 degrees, and the sine of 90 degrees is 1. And so this is the force the charge is feeling when it's in the B field. All right, now when it goes into a circular path, you go back to F equals ma, but for circular motion, it's mv squared over r. And that's equal to qvb. Put up a wall here. And you can see one of the v's cancel. And a really simple measurement to make in this experiment, the dependent variable, would be the radius here. So we're going to solve for radius. We'll put that up here, and then we're going to take these two guys and put them down there. And that's going to be mv over qb. So look what it says. If you make the B field bigger, right? The radius is going to get smaller, smaller, smaller. Why? Well, because it's interacting with the B field. Bigger, then the radius is going to get bigger. Why? Momentum. You see up on top? That's momentum on top. You see mass times velocity. The more momentum you have, the harder you are to turn. So this will go into a bigger circle if it has more momentum. So you can see you can change the V, you can change the B in the experiment, and then you can change these like one time. These controls right here, you can change like one time. We'll use those as controls. All right? So that's the math behind it. Now there's a cool thing that happens if you don't make the sine of 90 degrees, but some angle in between, like let's say you had 30 degrees. Well, if you did that, then you have the B field. Okay, let's say B field's going like this, and the velocity is like that. And there's the angle theta. So you would have a component right here. This would be V cosine of theta. And then this guy over here would be V sine of theta. So if you're going at an angle like this, then the charge will go into a circle like this, but then it would travel in the direction of the B field because there's a component that's parallel to the B field, and there's no force if your velocity is parallel. So you go into a helical path. All right. The northern lights do that. So on the Earth, we have magnetic bottles that surround the Earth, and the charges go up and down, back and forth, North Pole to South Pole, in a helical path. Then they turn around because it's not a totally uniform B field. Come back, and then sometimes there's so much charge in there, it spews out over the poles of the Earth and lights up the skies. Those charged particles, moving so fast, light up the sky like a neon sign. All right, so let's look up here. So this is going to be a little bit of review. We put most of it on the board. So the Lorentz Force Law, we already went through that. And you can see this is a case where the velocity has a perpendicular piece. By the way, the B is going like this. So this is the parallel piece over here. And then this is the perpendicular piece. So perpendicular, you go into a circle like this. And the parallel, you go constant motion like that. Okay? So we're interested just in the perpendicular. Okay, we're not going to study the constant motion like that. Now, if you want to get the speed of the particle, you have to take the energy that the charge is going to have. And he's going to get the charge, you're going to take the charge multiplied by the voltage. And the voltage is between 100 and 400 volts. So you take the charge times that number, and that's potential energy. And then once it goes through that potential, so if you look over here on the picture, we create the electrons right here in what's called a electron gun. And what it is, a hot cathode right here, a hot filament of a light bulb, is going to create a bunch of electrons that are so hot they're like flying around the cathode like bees around a hive. And then you're going to make this guy over here like 400 volts. So when these guys are flying around like this, they see that 400 volts positive, and poof, everything disappears. Okay? And then it gets accelerated over here. And then there's a little hole inside this little cylinder. There's just a hole. Otherwise it's a solid cylinder, and the beam comes out like that. Here you can see it down here. So you see, this is a cylindrical can, and then there's a hole. In fact, they put a couple holes so you get a really nice straight beam. Okay? And this is how you get the velocity. So the potential energy goes into kinetic energy, and that's the equation for the velocity of the charged particles. Now, Thomson is the guy who discovered the electron doing this experiment right here. Now, he was able to get the velocity because he knew what the voltage was. All right, and he was able to get the velocity. I'm sorry. He knew the voltage. He didn't know the charge. He was able to get the velocity by measuring the radius of the circle. So he knew this number right here, and then he knew the voltage because he set the voltage. All he could determine, though, was that number Q over M, and that's called the charge to mass ratio of the electron. So when he discovered the electron, he discovered only the ratio of those two numbers. Someone else would have to figure out another experiment just to measure charge. Okay? Anyway, that is the setup right there. And the last thing, there's a lot of stuff in this lab, just theoretical stuff. If you take a coil of wire, now I have a coil of wire right over here. If you take a coil of wire like this right here, and you send current through it, what'll happen is you'll have a B field that comes out all around this thing like that. So it's non-uniform. Non-uniform. Okay? And if you just have one all by itself, and let's say you just went right down the middle like this, and you wanted to see what the B field is, and you plotted it, it would look like that. Okay, very non-uniform B field. All right, it goes to a maximum and then goes down like that. And then, if you have another one, same thing. And you separate them by the diameter of the ring, the coil. When you put those two together, those are vectors now. If you take the vector field from both of those and you do the superposition on it, you get a really flat field within almost like half the diameter of one of the coils. And that's what they do. So you see right in here, you can see that this tube right here is about half the diameter of the coil. And so right where that's sitting in the middle between those two coils of wire, both carrying the same current, which produces the same magnetic field, you get a fantastic uniform B field. And that was invented by a guy named Helmholtz. And you're going to study this little equation next week. We're going to talk a little bit more detail about actually producing a B field from a current flowing through a wire. All right? And so all these words right here, by the way, I post these PowerPoints. You can go back and look at them. So there's a couple of notes in here just to make sure I cover everything. But this particular lab, I do a lot, so I know it pretty well. All right, and this is the experimental setup, and in this particular setup here, these guys have an ammeter here, a voltmeter here, and these are really different from the ones we use in our lab. And then down here, this is a power supply, and then this is 2 power supplies right here. Well, I have 4 power supplies in one right here. So my setup's a lot cleaner than the one you're seeing on the screen. You see I got my 2 little meters right here, and then I have my power supply down below. Each one of these VU meters is a power supply. And then up here is the unit. Okay? And so from there, we're going to actually do the experiment for you, show you how it's done. And that's the second video. So I'm going to check out of this one, the background, and move right along to the experiment. So we'll see you very, very soon.